Gradient for the t function. Anyone got it? What was that? How about it was at 821? What was the point? 821. So what was the gradient at 821? Anyone remember or have it? Negative 0.04, okay. 0.2. Like this?
Yeah.
Okay, has all the homework turned in? Pass it in. Get your heading right. Okay, so then the very last question was asking, so this would be, if this is the gradient, this would be what? The direction of max in the room from that point, the direction of max increase of temperature. And so if we wanted the direction of max decrease of temperature, what would that be? Exactly the opposite direction, right? And that's kind of the same as what we saw before. But then when I said, it's negative. So the last question says then, oh, and so then there was a question in there that just said, if you go 1.25 feet? Feet? If you go 1.25 feet in that direction, how much will the temperature change? So the intention of that problem was that you would think, oh, that's just dy equals mdx. I'm using x and y loosely. I'm changing 1.25 in some direction, and I want to know how much the temperature changes, dt. So what do I need? I need the rate of change in the direction that I'm going, whatever this direction is. So how would I get the rate of change in the direction of the greatest max or greatest decrease of temperature? How do you get the rate of change? You take, what about the gradient? So this is the rate of change? The magnitude, right? So that rate of change that we need is the opposite of the magnitude of the gradient. That's a rate of change. That's the rate of change in the direction of greatest decrease of temperature. And so the question said, if you go a little bit in that direction, right? That's like if you change a little bit, then what's the change in temperature? Well, that's just the rate times 1.25. So it's just an application of the way that we're framing rate of change, right? The way that we're framing rate of change is given any change in the independent, what's the change in the dependent? Well, your change in independent now is this 1.25 in the direction from that point. And so then you need the rate of change in that direction. Well, that's the opposite of the direction of the gradient. Yeah?
I think that we got the...
Is there something wrong up here?
The two temperatures mixed up. Like, I think that they should be different. Like,
This gradient's wrong?
yeah, no, they're right, but the negative are switched. Should we switch?
I think the first one's negative, the second
The
one's
first one.
Oh, this is the
Yeah.
direction of, oh, got it. Thank you.
This right.
Understand. All right.
Sorry about
No, that's good. I'm glad you mentioned that. Thank you. So this is the direction of the gradient, and this is the direction of max decrease of temperature. Sweet. Okay, good. Thank you. All right, so in any case, the magnitude of either of these is going to be positive, and then you're going to take the opposite of it to get the negative, and you're going to multiply that rate of change times your little change in independent, which is in that direction, to get the max change in temperature. So that was the intention for that problem. Does it make sense? Okay, and then the last question was, what about directions of, so here I am at 821, what about directions of 0 rate of change? Well, this is different because before we were dealing with what? Surfaces, z is a function of x and y, and our direction was framed in the xy plane with the unit circle, right? and our direction was a two-dimensional gradient, right, or 1 theta, right? Well, now this is different because the direction isn't in a plane, but the direction is in any as in R3. So say here's the gradient t, suppose, and then here's negative gradient t. So remember here, if we had the gradient and we had the opposite of the gradient, then how many ways could we go to get 0 rate of change? 2, right? And then we've showed that those are both the 2 ways that are orthogonal to those, right? So the 2 ways orthogonal to the gradient and the opposite of the gradient are the directions of 0 rate of change. So if we're looking for a direction orthogonal to these in space, in 3, so now from A21, we can go in any direction, right? And so now what's orthogonal to those 2 vectors? So how many vectors are orthogonal to those 2 vectors in space at A21? Infinite. And what characterizes those infinite directions? The plane, right? So there would be a plane such that every vector parallel to that plane at A21 would be orthogonal. So if the question is like, what direction could the bug fly to experience 0 change in temperature? Well, that's in any direction parallel to this plane. In any direction parallel to this plane. So we could just so that's an infinite number. We just call it ABC. So now we want to kind of qualify what vectors fit this. Well, ABC would have to be what? Orthogonal to this. So mathematically, how do we show that? All right, are you with me? Is this making sense? If I'm losing you, ask. But I'm just saying any vector parallel to this plane is going to be orthogonal to the normal vector of that plane, which is the gradient. So mathematically, how do I frame what that vector is? Dot product with what? This. 0.04, negative 0.2, and 0.12 would equal 0, right? So if we work that out, we get over here. We would get 0.04a minus 0.2b plus 0.12c equals 0. So I've got this vector ABC, and it has to the components of ABC have to satisfy this equation, right? They have to satisfy this equation. Is this the equation of the plane? No, this is not the equation of the plane. This is just a relationship between A, B, and C that satisfies makes ABC be parallel to that vector. So if I have this one equation and these 3 variables, then how many what's called degrees of freedom do I have, right? How many degrees of freedom do I have if I have 3 variables and 1 equation? You know what that means, degrees of freedom? Like, you can choose how many of these variables to be anything you want. 2, right? You can choose A to be anything you want, and then B to be anything you want, but then, once you choose your A and B, then C is determined, right? C is determined. So C would be, what, 0.2b minus 0.04a divided by 0.12. So that is how we could characterize every vector, every direction that the bug could fly from A21 and experience 0 change in temperature, because this is all vectors that are orthogonal to that one. So you can choose the x direction to be anything you want, y direction to be anything you want, but then once you do, then z is determined by that relationship from the dot product. Does it make sense? Are you close, at least? Yeah.
Would it have been right to parameterize that plane as 2 vectors?
Parameterize.
Span of 2 vectors.
So maybe I'm not sure. I'm not sure what you mean.
So like that plane, the plane is the span. That plane is the span of 2 vectors, right?
Okay. It's
So it's
meaning-
some vector times t plus some vector times s, right?
some vector times t plus some vector times s. And are both those vectors in the plane?
Yeah.
So if you have 2 vectors in the plane,
Plus the original, like 8
the 8, 2 you don't need. But so what did your final answer look like then? Because what you need is a set of vectors. If your final answer is a set of vectors that's the same as these, that's right.
5, 1, 0 times t plus negative 3, 0, 1 negative 3, 0, 1 times s.
So you're saying that negative 3, 0. So this would be
Yes,
so
right.
both of these then would be possible directions to go, right? If you set t equal to 0 and s equal to 1, you get this. S equals, so let's just check. If I do negative 3, 0, then do I get 1? That's the question. Yeah, you do. And then if you do 5 and 1, do you get 0? So 5, 5. Yeah, looks like it's right. Yeah, and so you also have 2 degrees of freedom, right? You're picking t and s to be anything, and the resulting vector. So that's a different way to do it. Yeah. Do you see how I checked it?
Yeah.
Set t equal to 0, then that vector has to be. So I've made negative 3, b 0, and then I got 1.
Yeah.
Same thing with this one. I made a5, I made b1, and I got 0. Yeah.
So moving orthogonally to the gradient does give you a 0 rate of change?
Yes. Yes, that's a big theme that we said, right? So in R2, so when you have a surface and your direction is in R2 and it's just like an angle direction, then that's these 2 directions, right? So alpha of 0 is the direction of the gradient. Alpha of pi is the direction of, meaning the opposite direction of the gradient. So then your other 2, alpha of pi over 2 and 3 pi over 2, gives you 0 rate of change. And then that's consistent with how the contours work too, right? So the max rate of change is perpendicular to the contours. Perpendicular is staying on the contour, right? So it's 0 rate of change. Other questions? Okay, so you were reacting back there. Is this what you guys did? Something like this? The second one? Or no? So both of these are valid forms. Where am I? This and this are both valid forms to answer. No? Does it make sense now? Okay. All right. So like I said, so the majority of the test covers, like the main themes are, the last main heavy emphasis is this stuff, directional derivative, okay, and everything to do with it. And then since the Monday's lecture a little bit, today we're doing optimization. It's not on there, okay? So today's stuff is not on there, and the optimization homework we'll make it due next Wednesday, okay? So then the only thing you've got to do before Friday is study for the test, okay? Hopefully you've started already. Questions on this example? Important example. Does it make sense? Okay, so we were here on this problem. We had said we want to identify values of local max, local min, and saddle points. And so we said those are the critical points where both the partial derivatives are 0. Okay, and so then I set the equal to 0, and then we found what made f of x 0. So either x equals 0 or y equals 1 made the first partial 0. So then I went to this, partial with respect to x. So I went to the partial with respect to y, and I put x equals 0 in, and I found out what y needed to be, and that was either 0 or 2. So there's our first two critical points. And then I took that y equals 1 from the partial with respect to x, and I put it into the partial with respect to y to see what x would need to be to make that 0. And that was plus or minus 1. So that gave us for the other two critical points where y was 1, and so x was plus or minus 1. So then we said we wanted to figure out what kind of critical points, and that was consistent. That the fact that we got 4 was kind of consistent with our just initial observation of the surface. And so then we wanted to look at, for each of these, let's calculate the determinant. So we can kind of make a table for that to make it go a little faster. So here's our critical points. And so we're going to find what is fxx. We really need fyy and fxy, and then d. So first we got to find fxx. What is fxx? Write that down. fxx, what is fxx? 6y. All right, so 6y. Let's just go right down the table here. 6y equals, for this one, for the point 0, 0, 0. 6y at the point 0, 2. So 6y equals that. Thank you. I was just taking somebody's word for it. Thank you. 6y minus 6. So therefore, fxx at 0, 0 is? That's better. Okay. At 0, 2? Positive 6. At 1? Or at 1, 1? At 1, negative 1, 1. Are we good? All right, what's fyy? Now that is not always true. That's just coincidence for the symmetry in this function, okay? fxx does not normally equal fyy. Don't get that impression. Okay, so we're going to have the exact same values. Are we good? What's fxy? So this is the partial with respect to x, then with respect to y. Just 6x at 0, 0, at 0, 2. Okay, and now we can do d. d is this times this minus this squared. So at 0, 0, d is 36, 36, negative 6. No, squared, right? Negative 36. And so then we use our about the discriminant. So our conclusions about the discriminant. So did we do all the math right? So type. So when d is positive, it means local max or min. And how do we tell? We tell by the second derivative, right? So if we have a local max, then what is the first derivative doing? What is the first derivative doing? If we have a local max, the first derivative is decreasing. You got rate of change that's getting less positive or more negative, right? So that's local max. So therefore, the second derivative, if the first derivative is decreasing, first derivative is negative. So what do we got here? That's a max, right? Because d is positive and our second derivative, so our rate of change is decreasing. So we're getting less positive and more negative at the top. That's a maximum. All right, what about here? So d is positive, but now our second derivative is positive. If second derivative is positive, that means, what about the rate of change? Less negative rate or more positive rate? That would be a min. So does that make sense? And then d is negative? Saddle automatically. but not sad. Saddle, but not sad. Okay, so that goes to that should fit right with our picture here. So at 0, 0, we got the max. At 0, 2, out in the x direction, we got the min, and then the two saddles at 1, 1 and negative 1, 1. So the picture is matching perfectly with our conclusions. Does it make sense? Any questions on that? Okay, so now what if, yes please?
Will the saddle always be at fx 0 at 5y 0? Or no?
Yes.
Or unless.
No, because if you're so for this particular okay, so for this particular saddle, you have the minimum in the direction like of what xy, and the maximum in the direction of orthogonal to that. So if the whole thing was turned pi over 4 or 45 degrees. Then you'd have one of them would be negative and the other would be positive, right? Does that make sense? So because our minimum and our maximum are exactly at 45 degrees to the x and y axis, that's why they happen to be 0 in this case. Does that answer it? Yeah, so if this saddle point was just turned 45 degrees, you'd have one of your second partials would be positive and the other would be negative. Because it would be, you'd truly have the maximum in either the x or y direction and the minimum in the other. So that's not necessarily true. Other questions? Okay, so then what if this function was some real world thing, some function that was giving us some real quantity, which would be the z-coordinate, given some combination of x and y, and then in the real world, the domain was restricted. So when we draw it in R2. To y equals 2x, x equals 2, and y equals 0. So in this application, this real world problem, only ordered pairs that fall in that region make sense. Okay. Okay. So we want to now. What we want to do is want to find what's called the absolute max. This is from Calc 1. The absolute max and absolute min. When of the values of z, whatever that quantity is, when we restrict to that region. Okay, so when we're inside of that domain for ordered pairs x and y, we want to find absolute max and absolute min. And so do you remember in Calc 1 where the possible places where we could find those were? There are different kind of candidates for where that could occur. So where could the absolute max and absolute min occur? Actually, there's kind of two things, right?
Could be at the edge of the region.
Yeah, so at the boundary, right? The boundary, if it's going up in one direction and then you cut it off, then the max or the min could be at the boundary. So before, like in Calc 1, that was like the endpoints, because our region before was just like an interval. So we checked the endpoints, right? But now it's like we check the whole boundary of the domain to see if there's a place where it gets the absolute highest or lowest, and then where else are possible values of absolute max or min? Critical points, right? So this should be familiar from Calc 1. Yeah.
So where did you get those restrictions from? The x equals 2?
I said this is the problem. I gave them to you, so they're given. So the function is given as the same function we had before, and we say suppose this function only makes sense for this domain. Okay, so it's given. Yeah. Okay, so the critical points we say. Okay, so what critical points apply then? What critical points do we want to check? So we're going to make a list of, over here, we're going to make a list of possible or candidates for absolute max and absolute min. And those candidates are going to come from the boundary, and they're going to come from critical points. So these are candidates for absolute max and min. And so, do we have any right off the bat? Okay, so 0, 0, in fact, is both, right? 0, 0 is a critical point, and it also is on the boundary. So certainly 0, 0 is going to be important. Any others? 1, 1. What about the other two critical points? Outside of the domain. So you can just throw them out, right? You can just throw them out. 0, 2, and negative 1, 1. You can just get rid of them, because if you're looking for the absolute max and min in this region, then those wouldn't apply. So that's our critical points that apply. So then the other things we have to do, so we're done with that, so we have to check the boundary. Well, now the boundary before, in R2 and Calc 1, I was just checking the two endpoints, right? It was an interval. But now checking the boundary means checking along there, and checking along there. So now you have three little Calc 1 problems, right? So what's true about this boundary right here? What is this right here? Y is 0, right? So we're going to take y equals 0, the first boundary, y equals 0. So now we're doing the boundary here, boundaries, y equals 0. And we're going to find the trace of our function at y equals 0. What was the function? Does everyone have it? Thank you. 3x squared y
Plus y cubed.
plus y cubed
Minus 3x squared.
3x squared
Minus 3y squared.
minus 3y squared. Thank you. Okay, there's our function. So now, plus 2, thanks. We're going to restrict this to y equals 0. So when we restrict this to y equals 0, we really are talking about f of x comma 0. Right? We're saying we just want a curve now. The trace of this surface where y equals 0. And what will that be? Question?
For the 3x squared, there should be a y after.
Okay, thank you. Yeah. Very important. Would have changed everything. Thank you very much. So f of x0 then is? Negative 3x squared plus 2. Right? Because so you're just going to plug in y in that function, and you'll get this curve, which is the intersection of what y equals 0 and the surface. You know, this curve. And so now you're going to do a little, and that's from x from what to what?
0 to 2.
0 to 2. So now you have a little mini optimization problem, Calc 1 optimization problem. You're going to optimize this function from 0 to 2. And what are the possibilities? Critical points and endpoints, right? So now you have to see if there's any critical points along that boundary, and you're going to check the two endpoints. So let's just put the two endpoints. We already have 0, 0. So what's the other endpoint here?
2, 0.
2, 0. That's going to be a candidate, right? Because that's an endpoint of one of our boundaries. So we'll put 2, 0 there in the mix. Did in red. Now, is there any critical points between 0 and... Jeez. Sorry. Are there any critical points between 0 and 2? Well, how do we know? Take the rate of change, right? Rate of change is negative 6x. Set it equal to 0. We get x equals 0. That's an endpoint. There's no critical points in between, right? There's no critical points in between 0 and 2. So we're done with that boundary. Next one. X equals?
2.
X equals 2. So we're going to have a little Calc 1 problem along x equals 2. We're going to find the trace of the surface, the intersection of x equals 2 and the surface. And that's going to be from y equals what to what? This is y equals 2x, remember? So that'll be from 0 to 4, right? So right away we'll have 0, 0. Or sorry, 2, 0 we already have. So there's another, going to be candidate is going to be at. What point is that? 2, 4. Going to be another candidate of possible absolute max and min. But then we have to see if there's any critical points in there. How do we do it? Find the equation of the trace, which is, this is going to be f of 2 comma y. 12y
plus y cubed
plus y cubed
minus 3y squared minus 10.
plus, that was over, plus 10.
Did you just also, did you account for the minus?
No, minus 10.
It is minus 10?
12 plus 2.
Minus 12 plus 2, so together makes minus 10. So it's simplified? Yep. And then that's from, what, 0 to 4? We already got those endpoints in our list, 0, 0, and, 2, 0, and 2, 4. So now we have to see if there's, any critical points between 0 and 4. All right, let's hold off on that. Let's get the other one started, and then I'll let you do it while I do attendance. So then we have, what's the last one? Last boundary is y equals 2x. So we're going to need the trace of f of what? X, 2x. So what you're going to do is you're going to, and that's going to be from, and that's going to be in terms of x, so x will be from 0 to 2. We already have 0, 0 in the list here. We already have 2, 4 in the list. So the last thing to do then would be, so what is your task? Critical points on the line x equals 2. Find the trace of y equals 2x on the surface, and find critical points on that one. And any critical points on x equals 2, or that y equals 2x, will also then be candidates for absolute max and min of the whole surface in that domain. So before I set you loose, any questions? Did you follow all that? So like you have a little Calc 1 problem on every side of the boundary, where you do the endpoints and you do critical points on each segment of the boundary, plus the critical points inside the domain. Okay, work together so you don't, if you make you can check to not make mistakes and dig too big of a hole for yourself. 5/7, 10/7. So I found a critical point on this y equals 2x of 5/7, 10/7. Did you find that? Someone else get that? One, at least one? And no critical points on x equals 2, because that was actually, gives you an, there's no real solutions to that. So then we got 0, 0, 1, 1, 2, 0, 2, 4, and 5/7, 10/7. I wrote it right there, perfect. And so what are we trying to find? How are we going to know? Yeah, get the z value for each. So find the z value for, these are the only possible ones. There's 5 points, 3 corners, that critical point inside, and this critical point on this boundary. Those are the only 5 candidates for the greatest z of all these xy order pairs and the least z. And so we just plug them in into here. So let's let the computer do the work for us here. So we want f of,
You need a y.
thank you, thank you, thank you, thank you. Am I good now? So we want f of 0, 0. F of 1, 1. Two, 0. Two, 4. And last but not least, 5/7, 10/7. Okay, so if I could see those are where we can see. So here's my z values for all those points. Absolute max is 54 at that upper right corner, right? At 2, 4 is when the z gets the highest. Absolute min 2, 0 on the x-axis at negative, and that the value of z, the lowest it gets is -10. Okay, does the process make sense? Yes, please.
Sorry, I missed it. Which one did you say had no real value?
Oh, when I did the x equals 2 boundary, so when you do x equals 2, I end up with the quadratic y squared minus 2y plus 4 equals 0 along x equals 2.
Okay.
And there's no y that does that. So that leaves something like that. So along this boundary right here, there's no critical points. The only critical point we got in the middle of a boundary was this one. The only critical point in the middle of the region was this one. And that was the 1, 1. Okay, so it's kind of a lot of tedious work, but make sure you have an image in your mind that it all makes sense together. Anybody have a question?